Hello, my name is Alphan Uzun. Today I'll be introducing you to my Physics 101 project, finding spring constant with different equations in real life. Main purpose of this experiment is to prove the scientific theorems about springs in a real life scenario. Physically, we're going to be using Hooke's law, period for oscillating springs, and K equivalent for connected spring systems. For our experiment, we are using a 15 centimeter ruler, two springs with two different spring constants, have different types of masses, and the timer we have in our phone. For the part A of our experiment, we'll use Hooke's law to calculate the K of each spring. So let's start with the first one. For our first spring, first we found our equilibrium position and mark it down. Then we are going to be applying masses to the system in order to see if it elongates when the weight is applied. And we're going to be starting with 200 grams, then we're going to be increasing that by another 200 grams for 5 other mass values. Let's see what happens when we apply it. We can see that it grows, like it has gotten away from the equilibrium position, and we mark that point as well. And in the end, we're going to be measuring these results for each of the 5 other mass values, and then we're going to be finding a K value for each spring by using Hooke's law. For finding the second spring's constant, we used a similar approach to the spring one. We used Hooke's law, however, this time we incremented the masses by 50 instead of 200 grams. And with the same calculations, and results can be seen as all these results show a near linear correlation with weight attached and the displacement, giving average constant value for S1 14.19 and S2 59.24, which shows the accuracy of the Hooke's law. We're going to be experimenting on springs that are connected in parallel. In this part, we'll try to find the K equivalent by using the simple harmonic motion period formula of springs. In this part, we're going to be starting with 600 grams first applied to the spring system. Afterwards, we're going to be incrementing this by 100 grams each and calculate for 5 other masses. In the end, we're going to compare whether K equivalent system for springs that are connected in parallel fits true to our results that we found in part A. For measurements, we oscillated the system 5 times and take the average for finding the period. And the results can be seen as this. Looking at the results, a near linear relation can be seen with t squared and masses that were attached to the spring system, which shows the accuracy of the equation for period in spring systems. Another point to observe is that whether the summation of the k's we found in part A is equal to k average of the system because of the K equivalent formula for parallel connected spring systems. As a result of part B, we found K average as 71.42, but when this is compared to the summation of K's we found in part A, 73.43, another percentage of 2.74 can be seen. However, it should be noted K of the system in part B is bigger than any of the values of S1 and S2, which again shows the accuracy of the formulas. For part C, we're going to be experimenting on a spring system that is connected in series. We're going to find the K equivalent of the system by using simple harmonic motion's period formula for springs. For this experiment, we're going to be starting with 100 grams applied to the spring system. Then we're going to be incrementing by 100 grams for 5 other different masses. We're going to oscillate the system 5 times, then take the average of those 5 times and find the periods. And in the end, we're going to be comparing these results to the results we found in part A. Results can be seen as... Looking at the results at part C, a near linear relationship can be seen with t squared and masses that were attached to the spring system, which shows the accuracy of the equation for period in spring systems. Another point to observe is that whether the results we found in part C holds true when we compare these results that we found in part A for K-equivalent formula. As a result of part C, we found K average as 10.72, but when this is compared to summation of the results we found in part A, an error percentage of 3.86 can be seen. However, it should be noted that K of the system in part B is smaller than S2, which has a bigger K value found in part A, which again shows the accuracy of the K-equivalent formulas. Moreover, if the results of part C and part B are compared, it can be seen that how K of a system can affect the motions period using the period formula for spring systems, and results fit the criteria as period values become smaller while K values are getting bigger. In the conclusion, first I want to mention the error margins. This was an experiment done in real-life circumstances, so there were many other influences, like friction and loss of energy. However, they were not put into consideration, which can cause an error margin, like I said. Also, some of the measurements, such as time and displacement, were made mechanically, which can cause again an error because of the human factor involved. Lastly, for errors, all of the calculations were rounded to the second decimal point, and exact value of gravity was not used. 9.8 was used instead. To sum up the experiment, in this experiment we found out that as the force applied to a spring increases, its displacement from its equilibrium position also increases proportionally. To add up, period of spring's motion is related to the mass attached and the K equivalent of the system, which can be approximated by their respective formulas. Most importantly, we tested the formulas of springs, which were found to be credible sources while approximating the values of spring constants.